Linear modelling is where we plot a straight line through our data points and try and find out more information from that line than we had before. Now, of course, a straight line is not always appropriate for many different data sets, and there are many other models that might be better for us, such as the exponential, the quadratic, and many more. But in this section, we're just dealing with the linear model, and we're looking at that in some detail. We're going to be looking at how to use it and the dangers and pitfalls of using it. So these are two underlying themes that go right through this whole section: how to and be careful. So that's why I've called this topic linear modeling. How good is the model? That must always be in our mind if we are using any type of model, but for today, for this topic, we're just looking at the linear one. It's not a matter of just knowing the techniques and blindly applying them. We have to always be asking, is this a useful model for these data? And so that's an important theme of this topic. So we're going to break linear modeling down into three main areas: correlation, the line of best fit that we try and put through the data points, and then between and beyond the data points. Correlation. Correlation is an attempt to find out if there is some sort of mathematical connection between your two sets of data, between your two variables. And if two variables are correlated, then if you change one, you've got a fair sense of how the other is likely to change. That's what correlation is about. So we're going to look at characteristics of correlation, the correlation coefficient, and a very hot topic, causation and correlation. Firstly, the characteristics. The interesting thing here for us is to find out what direction is the correlation in? Is it linear? How strong is it? And have we got any outliers in our data set? So let's quickly go through those main characteristics. The direction, that is just positive or negative. That's the slope, the gradient of the straight line if we plot it, once we plot the line of best fit. So here we have positive correlation because the gradient is going to be positive of the line we fit. Here we have a negative correlation. So there's nothing really new there. We want to know, though, before we go any further in using linear models, well, how linear is it? And initially we can talk about it as being a linear model or a non-linear model. For example, this looks reasonably linear. We can plot a reasonable straight line through there and feel reasonably confident about that. Out here, they're related in some way, but it's definitely not a linear relationship. So to apply a straight line for these data would be a big mistake. So we have to look at our scatter plot before we go any further. But if we're reasonably happy that putting a straight line through the data looks reasonable, then we go ahead. And we can talk about the strength of the correlation. If once we put our line through, the points are all quite close to that line, we call that strong correlation, whether it's positive or negative. If we put a line through, our straight line through the data points, and there's still quite a bit of scatter around that line, we might say that they are moderately correlated, or if the points only just form a very vague straight line, we say they are weakly correlated. And in fact, if they're completely scattered around the plane of the graph, then we say they're not correlated at all. Another important point, particularly in any practical work and such as your project, if you're going to be using linear modeling, is to look at outliers. Outliers are points that we think may not actually belong. There might be something wrong with them. They may not belong to the data set. So for example, suppose that we'd graphed this, and we see at both ends there are some points that we're not quite so comfortable with, perhaps. We can fit a reasonably good, well, a very good straight line through most of the points, but then at both ends there are these points that are tailing off. It might be very tempting to call them outliers and get rid of them, and then we've got a nice straight line, haven't we? But that's a big, big danger in doing that, because if we just tend to remove all the points that don't fit the straight line, all we're doing is finding what we're looking for. So we must be very careful of that. It's quite possible that these data do in fact tail off, go into a reasonable straight line and then tail off again. And a sort of an S-shaped curve perhaps. That's quite possible. And if we start removing lots of data points, then we are really misleading ourselves and whoever we present these results to. However, if you had a data point, just one isolated data point stuck up here, say, a long way from all the rest, you might be inclined to remove that one. But you still should be very, very careful about removing any data. And in fact, the safest golden rule is that if you've got some points you think might be outliers, go back and have a look at them. Have a look at how they were collected. See if something was wrong in the recording or the measurement or something. And then often you will find something then, and you can either remeasure for that value or just delete those points. But it's very dangerous just to delete a point because you think, well, it doesn't sort of go near my straight line. Maybe that's actually showing you something really important you didn't know about. So outliers, it's easy to get rid of them and find what we're looking for, but that is not a good thing to do. You should really only remove data if you have gone back and looked at it and can see that some mistake was made or there's some reason for it not being appropriate in this particular data set you're working with. Here's another example. These data, if you restrict it enough, you can get a very nice straight line through it. But in fact, this might be a much more curvy line indeed. And if you didn't force a linear model on the data, you might get a lot more and a lot better information out of it by putting some sort of curve through the data. So that's another example of just being very, very careful of removing outliers. Okay. Now, we talked about the strength of the correlation, and loosely we can, or subjectively, we can call it strong, medium and weak. A nicer way is to get an actual measure of the correlation, and this is where the correlation coefficient comes into play. The correlation coefficient, which your calculator or other software will calculate for you, gives exactly what we're asking for here, a measure of how strongly the two variables are correlated. So, and also the beauty of it, it tells us straight away whether it's a negative or positive correlation. So if the gradient of the line is negative, the correlation coefficient is negative. If the gradient of the line is positive, the correlation coefficient is positive. And the size of that, not the sign, but just the size, the magnitude of the correlation coefficient tells us how strong the correlation is. The closer it is to 1, and therefore to -1, the stronger the correlation. So a -1 or a +1 are telling you that these variables are perfectly correlated. If you change one, you know exactly what the other one will be. As the correlation coefficient drops to -0.9 or 0.9, there's a bit more scatter about the straight line, but they're still pretty strongly correlated. And as the correlation coefficient gets less and less, they get further and further away from forming a nice straight line. Here we are at 0. There is no correlation at all, they're just random. And so that's the beauty of the correlation coefficient. Calculating it, well, it looks a bit hideous, and you won't actually be needing to do this, but there is the formula for you. It's not really as complicated as it looks, but there's no need to do that by hand. Your calculator's got that built in, so you just put in the data, it will give you the correlation coefficient. But that's just so you know, it's not some great mysterious thing. It's just taking each x value and seeing how far away is that from the mean, multiplying that by the corresponding y value and how far that is away from its mean, and just dividing through by those squareds to normalize things back so that it goes from -1 to 1. So that's all that is about. You don't have to do it, but it does help to have some idea of what